So continuing on with our discussion of the mean value theorem, I want to get sort of rigidly mathematical here, and I want to just address the fact that the assumption, if f is continuous on the closed interval and differentiable on the open interval, that these two assumptions are completely essential to the mean value theorem holding. So what I want to show here is that if you're not continuous, it's possible for the mean value theorem to not be true. And moreover, if you're not differentiable, it's also possible for the mean value theorem not to be true. So let us hypothetically imagine a situation here. So let's first here, let's deal with if the function is not continuous. Is it possible to break the mean value theorem? Is it possible for the mean value theorem to not hold if continuousness is not a part of our function? Or in other words, is it necessary that continuity be a characteristic of our function in order to get the result of the mean value theorem? And I claim that yes, being continuous is necessary. And here is an example to show otherwise. So here is RA, here is RB, here are f of A, here are f of B. Now we know that there is an average slope between those. That is the slope f of B minus f of A over B minus A. That's not change in y over change in x. That's simply the average slope between those 2 points. That is the slope of the dashed line. And now, what if f wasn't continuous? Is it possible that the function would fail the mean value theorem? And I claim, yes, no doubt. Check it out. Imagine the function started off going like so. Note, the slope of this line is not the slope of the dashed line. The mean value theorem says that for some c in between a and b, the slope of the tangent has to be equal to the slope of the dashed line. But now, imagine the function jumped from that point, whoops, let me get right above here, how about to there, and then the function continued onward. Think about this. This function that I drew here in blue is not continuous. And by the virtue of it not being continuous and it jumping, we started off at a slope not equal to the dashed line, and then we proceeded at a slope not equal to the dashed line. And note, for no c between A and B is the tangent slope equal to the slope of the dashed line. And let me just write that out. The slope of the dashed line, f of b minus f of a over b minus a. So, long story short, if we're not continuous, it's possible for there to be a point where the tangent slope would not be equal to the slope of the dashed line. So then you might be wondering, but wait a second, is this possible when you're moving down the road in a car? Because if this was possible when you're moving down the road in a car, well then the mean value theorem wouldn't hold for you moving down the road in the car and the cop couldn't pull you over. But what would it mean for your function to be not continuous? That would mean that you're traveling down the road and getting to this point and then instantly teleporting to another position. Now, if it's possible in your car to teleport from one spot to another, then it is possible that if it's possible for you to teleport from one point to the other, then the cops can't pull you over for speeding because you were not speeding, you just teleported. However, if you're not teleporting and you're continuous, then you're going to be like the previous case, or will you? Because let's address the case of differentiability. Let's put that down here. What if our function was not differentiable? So I want to pose another question to you. Like the mean value theorem, as we stated, it said that f had to be continuous and f had to be differentiable. Let me ask the question here, because we just proved up in this bubble that being continuous is necessary. If you were able to teleport through time, if your function was able to jump, the satisfying statement of the mean value theorem would not be satisfied. And, well, in other words, you would be able to have tangent slopes that would be different from average slopes everywhere. What about if you weren't differentiable? Is it necessary that our function be differentiable in order for the mean value theorem to hold? And I claim, yes, you must be differentiable. And let me show you an example of a function that is not differentiable that fails the mean value theorem. So let's do the classic setup. Here's your A, here's your B, here's your f of A, here's your f of B, here's your point, there's your point, there's your average slope in between. Now, I'm actually going to draw a function here that is continuous. I'm never going to pick up my pencil all the way along, but the function that I draw is never going to have a tangent slope equal to the slope of the dashed line. So check it out. I'm going to go up like so. Note, nowhere along this path is the tangent slope ever equal to the slope of the dashed line, and then I'm going to harshly change trajectory like so. Interesting, right? Because here we have a function that is not differentiable, but now check it out. Let's ask the question. Is there any point between A and B where the tangent slope equals the slope of the dashed line? Oh no, because here the slope is greater, here the slope is lesser, and never is the slope equal to the slope of the dashed line. So here, there is no C between A and B where f prime of C equals the slope of the dashed line. And let me just write that out. The slope of the dashed line is f of B minus f of A over B minus A. And what we show here is that if you're not differentiable, then the mean value theorem wouldn't hold. So you would have to be differentiable for the mean value theorem to hold, which is to say that being continuous and being differentiable are both necessary. If you're ever asked why the mean value theorem applies, it's because a function is continuous on the closed interval AB and differentiable on the closed or the open interval AB. Both conditions have to be satisfied. And now you might be wondering, with respect to the COP, you might be thinking, but wait a second, is this possible here where you would have a cusp on your function? Because if that were possible, then the COP couldn't pull you over, because the COP pulling you over was under the assumption that at some point along the way, your speedometer was reading the same value as your average speed. But here's the thing, for this to occur, you'd have to be going at a certain speed and then suddenly change to a completely different speed. So you'd have to be going at 60 and then in an instant be going 50. But that's not possible. Because when you're traveling down the road, if you're going from 60 to 50, you're going to have to hit every speed in between. Just like if the temperature goes from 60 to 50, it's going to have to hit every temperature in between. So the long story short is, when you're moving down the road in a car, your function of your position is going to be differentiable. And here's then the long story short, and let's close on this. Okay, we've got a function. We've got a certain position at A and another position at B. Between those 2 points, like between any 2 points, there is a line. That line has a slope. The slope is f of B minus f of A over B minus A. This is change in y over change in x. This is the slope of the dashed line. So let me just reiterate this, because I wrote it before, but I want to be very clear. This is the slope of the dashed line. And now, the mean value theorem says, if you have a function that is continuous, you're drawing it with no jumps, holes, or asymptotes, without picking up your pencil, and differentiable, no corners, no cusps, a smooth function, then there must be a point C where the tangent slope equals the slope of the dashed line. And now, let me draw here between these 2 points. And I actually encourage you, frankly, on your own paper, to draw a continuous, without picking up your pencil, line. Line is a curve, a continuous curve, from A to B, from f of A to f of B, that is both hiccup-free, no hole, jump, or asymptote, and corner and cusp-free. It's smooth. So you need a smooth, continuous path from A comma f of A to A comma or B comma f of B. And I'm going to draw this in here. The smooth continuous path like so. Note, this is continuous, no holes, jumps, asymptotes, and this is differentiable. At every point there is a tangent line. Never do you have a sharp change in slope. And the claim of the mean value theorem is that there's some point along the way where the tangent slope equals the slope of the dashed line. And if you follow along the function here, you can see that there is a point. It's about right here, where the tangent slope equals the slope of the dashed line. That is our C. And the long story short is the mean value theorem guarantees this. So to use the mean value theorem, you have to have a function which is differentiable and continuous. Continuous on closed AB, differentiable on open AB. But if you have something continuous on closed AB and differentiable on open AB, you get the mean value theorem as a result. We'll have one more video to go through an example, and we'll do some more examples in class, but we basically got a wrap on the idea at this point.